Welcome to Database Fundamentals. Today we'll be discussing view serializability, an advanced concept in database concurrency control. So first, we'll start with an introduction to view serializability definition. This is a correctness criterion for the concurrency execution of transactions in database systems. View serializability is more general than conflict serializability and is based on the view of data items by transactions. It captures equivalence between schedules based on read-write dependencies. View serializability ensures that transactions seal consistent states of the database regardless of concurrent execution. An important point to note is that view serializable schedule may allow more concurrency than conflict serializability while still maintaining correctness. So let's look at the formal definition of view serializability. Two schedules are view equivalent if they satisfy these three conditions. So first, we have the initial read condition. So if transaction Ti reads the initial value of a data item X in the schedule S, then Ti must also read the initial value of X in the schedule S prime. And then we need to check the read from relationship. So if transaction Ti reads X written by another transaction Tj in schedule S, then this must also happen in the schedule S prime. And in the last one, we need to check the final write condition. So if transaction Ti performs the final write on data item T, a data item X, in the schedule S, then the same transaction must also perform the final write on X in the schedule S prime. So a schedule is view serializable if and only if it is view equivalent to some serial schedule. And note that when we have like n transactions out there, there are actually n factorial possible serial schedule of these transactions. Let's better understand the key aspects of view equivalence. The initial read refers to a transaction regarding reading data that hasn't been modified by any previous transaction in the schedule. The reads from relationship defines which transaction's write operation is read by which other transaction. The final write identifies the last transaction to write a particular data item. So in simpler terms, the two schedules they're view equivalent if every transaction reads the same values in both schedules. So they're looking at the same values. And the final database state is the same in both schedules. So view equivalence preserves the external effect of transactions but allows for different internal orderings. So basically, we're allowing them to be run in an interleaved manner. And now let's discuss the steps to check whether two schedules are view equivalent. So we do this by definition. First, we need to identify all of the data items accessed in both schedules. So we may have X, we may have Y. And for each data item, so let's say we're looking at X, we need to identify the transactions that perform the initial reads on X in both schedules. And then we need to construct the reads from relationship for X in both schedules. In the end, we need to identify the schedules, we need to identify the transactions that perform the final write on the data item X in both schedules. So we need to do this for all data items. We need to compare these aspects across both schedules. The initial reads must match, the reads from relationships must match, and all of the final writes must match. If all of these conditions are satisfied for all data items, then we can arrive at the conclusion that the two schedules are view equivalent. Let's work through an example to test view equivalence. Consider these two schedules, S1 and S2. In S1, we have T1 reading and writing A followed by T2 reading and writing A, and then reading and writing B. In S2, we have T2 reading and writing A, and then reading and writing B, followed by T1 reading and writing A. So they're inherently the same transactions but different schedules. Let's analyze the data item A, and then we'll look at B. So in S1, T1 reads the initial value of A, and then T2 reads the value written by T1, and then T2 performs the final write on A. In the other schedule S2, T2 reads the initial value, T1 reads the value written by T2, and then T1 performs the final write. So we can see that these two schedules are not really view equivalent because the initial reads from relationships and the final writes are all different. Here's another example comparing two schedules S3 and S4. In S3, we have T1 reading and writing X, and then T2 reading and writing X, followed by T3 reading and writing X. In S4, we have T1 reading and writing X, and then T3 reading and writing X, and followed by T3 reading and writing X. For data item X in both schedules, T1 reads the initial value of X. However, the reads from relationship are different. In S3, T2 reads X from T1. So basically, the second transaction is reading a value that is written by the first transaction, and the T3 reads X from T2. In S4, T3 reads X from T1, and T2 reads X from T3. And in the end, we can also see that the final writes are different. So T3 does the final write in S3, while T2 does the final write in S4. So we can see that these schedules are not view equivalent either, because the reads from relationships and the final writes are all different. And now let's look at a view serializable schedule with a blind write. So we'll explain what is a blind write. So consider the schedule shown on the screen with three transactions, T1, T2, and T3. T1 reads and writes A, and then T2 writes A without reading it. So this is a blind write, followed by T3 reading A and writing B, and finally T1 reading B. So the analysis shows that T1 reads the initial value of A, T3 reads A from T2, and T1 reads B from T3. The final writes are performed by T2 for A and T3 for B. This schedule is actually view equivalent to the serial schedule T1 followed by T3 followed by T2, where T2's write to A is a blind write that overwrites T3's value. So this example demonstrates that a schedule can be view serializable even when the equivalent serial order difference is different from the execution order. So let's look at another example that highlights the importance of blind writes in view serializability. So basically, blind writes are allowed in view serializability, but not allowed in conflict serializability, because if we have blind writes, they will be in conflict with each other, and that will create a cycle in the precedence graph. So let's consider this schedule. T1 reads X, T2 writes X, T3 writes X, and then T1 writes X. We can see that T1 reads the initial value of X, T2 and T3 both perform blind writes to X, and T1 performs the final write to X. This schedule is view equivalent to the serial schedule T1, T2, T3, because T1 will be reading the initial value of X, and no transaction is reading the value written by T2 or T3 because of blind writes, and then T1 still performs the final write to X. So basically, when the blind write is happening, view serializability is allowing blind write, and it is not when the blind writes are happening, the read from write relationships are satisfied trivially. So this demonstrates how blind writes provide additional flexibility for view serializability. Let's consider some practical aspects of view serializability. There are several challenges in implementing view serializability because testing it is very computationally expensive, as we can see, because as we have to go for a given schedule, we have to check whether it is view equivalent to every serial schedule of the transactions. And in theory, there can be n factorial serial schedules. So it is an NP complete problem to test it. And it requires knowledge of all future operations in a schedule, and it is very difficult to enforce during runtime with dynamic transaction arrivals. The table on screen compares view serializability with other isolation levels. So view serializability offers strong isolation, but at an NP complete computational cost. So that's very slow. So this is mostly theoretical and rarely implemented. So conflict serializability is stronger and it is more restrictive, and it has polynomial time complexity. So basically, the time complexity of conflict serializability test is big O n squared, where n is the number of operations. So it is more practical and widely used. Snapshot isolation offers moderate strength at low computational cost and is common in modern database systems. So here are some special cases in view serializability. View serializability allows schedules that contain blind writes, as we have already seen, and anti-dependencies, and intermediate reads. A classic example of a schedule that is view serializable but not conflict serializable involves blind writes by transactions that do not need to be ordered relatively to each other. So consider the example. The first transaction reads X and then writes on X, and then the second transaction writes on X, and then the third transaction writes on X, and then the first transaction performs the final read. So this schedule is actually view serializable, and it is equivalent to the serial schedule T1, T2, T3. But obviously, it is not conflict serializable because the corresponding precedence graph will be having a cycle. So to summarize the key points about view serializability, view serializability is based on reads from relationships, final writes, and initial reads. Two schedules are view equivalent if they have the same initial reads, reads from relationships, and final writes. View serializability is more general and allows more schedules than conflict serializability, and testing for view serializability is NP complete, and it is very impractical for runtime enforcement, and that is why we always use, most likely we're using conflict serializability in practice. So while theoretically significant, most database systems implement conflict serializability due to the algorithm efficiency. Thank you for attending this presentation on view serializability, and I'll see you next time.